Our story begins in 1938, towards the end of the Depression, when work commenced on the erection of a new factory to manufacture radio set components for the Philips organization. Shortly after the outbreak of war, a part of the Mullard Radio Valve Company of Mitcham, Surrey, came to Blackburn, commencing with a staff of 28. As the war progressed, the demand for valves increased until by 1945 the number of employees had risen to nearly 3,000. With the return of television, the output of valves and cathode ray tubes increased rapidly. Feeder factories to supply valve assemblies were opened at Warrenhurst Road, Fleetwood, in August 1949, at Radcliffe Road, Fleetwood, in May 1951, at Waterfoot, Rawtenstall, in October 1953, at Lytham in February 1954, and at Blowick, Southport, in November 1954. New buildings were erected on the Blackburn site. This is part of the new wire factory completed in 1954 to produce high-grade tungsten and molybdenum wire. In 1955, the new glass factory was built. Over 500,000 glass components are produced here every day. In 1959, a chemical plant was built to produce under ideal conditions the large quantities of high-grade chemicals used in the making of valves. Huge quantities of hydrogen, oxygen and other gases are used in the manufacturing processes. To make the factory independent of outside suppliers, this plant was installed in January 1961. Blackburn Valve Assembly Department moved to more spacious accommodation in yet another new building in March 1961. About the same time, an office block was erected near the main gate. In this modern building are situated the personnel and purchasing departments. By this time, the largest valve manufacturing plant in Europe, the Blackburn Works, in 1962, provided employment in its various factories for over 6,200 people. Before going into the works to see some of the processes involved in the manufacture of a thermionic valve, let us take a look at the various parts of a typical valve and how they fit together, so that we may recognize them again later on. This is the bottom mica on which the assembly will be built. Next, the cathode. This radiates electrons when heated. Grids 1, 2, and 3. These control the flow of electrons passing from the cathode to the anode. Now the anode. This collects the electrons which have been passed by the grids. The top mica, which anchors the free ends of the other components. The heater to energize the cathode, and the metal strip to connect grid 1 to the base. Here is the base, which will be used to plug the valve into its socket. The cooling plates which dissipate heat from the first grid. Next, the getter, which contains a barium alloy. This material will later be used to trap and absorb any minute traces of gas which may be left in the valve. Here is the complete assembly. And finally, the glass bulb into which the assembly is sealed. Now let's go into the factory and see this same valve being assembled. We shall go through the operation step by step, and as each component is added, we'll have a look at the department where it is made. First, the bottom mica screen assembly. There are many shapes and sizes of micas, catering for the requirements of the numerous types of valve produced. They are purchased already cut to shape, but before they can be used, they must first be sprayed to improve their insulation properties. Samples are then taken from each batch and carefully inspected. Any batches which may contain faulty micas are rejected. In many cases, metal components such as brackets, screens, eyelets, etc. are attached to the mica at this stage. Here is a bottom screen being fitted. To the mica is assembled the cathode. This is a short length of nickel tube with a rim near one end to support and position it in the mica. And here is the department in which it is made. On this machine, the cathode is cut from a long length of round tube, the rim being formed at the same time. Here is the operation in close-up. The cut lengths now pass to a forming machine, which presses them into the required shape and size. On a later type of machine, the cathodes are made from flat nickel strip. These are known as lock-seam cathodes and are free from the chemical impurities sometimes introduced into the metal during the drawing of round tubing. In this scene from a research film, you can see the forming operation in slow motion. Now the cathode is coated on the inside with an insulating substance. This is to prevent shorting between the cathode and the heater. The cathodes are passed from a vibrating hopper down a metal tube to the coating station. The small rocker arm in the center of the picture positions a drop of the coating material near the end of the cathode. The liquid is drawn through the cathode by vacuum, so coating the inside. Moving now to a welding machine, we see a short length of strip metal being attached to the cathode. This is known as the tail and will be used to complete the electrical connections at a later stage. Other types of cathode are also made. This one is for a television tube. Valve cathodes, such as our EL84, are loaded into spray racks either by hand or by a vacuum loading jig and passed through to the spray room. In the spray room, the racks are placed on a conveyor belt and passed between spray guns. These coat the outside of the cathode with a chemical compound, which when heated gives off electrons. The depth of this coating and the evenness with which it is applied must be very carefully controlled, as these factors will affect the life and performance of the finished valve. After inspection, the cathodes are sent to the assembly unit. Next, the grids are added. In this valve, 3 are required. The function of the grids, you will remember, is to control the flow of electrons passing from the cathode to the anode. Grids are made from different kinds of wire wound in a long strip on a grid winding machine. As the machine spins round, it anchors the fine grid wire into notches made automatically in the backbone wires. After washing and undergoing heat treatments, the strips pass to the grid finishing section. Here, the strips are cut into separate grids and gauged to ensure that they are the correct size. The finished grids are placed into trays and passed to an inspectress. On the latest type of grid winding machine, all these operations are carried out automatically. The grids are wound, glowed to straighten the backbone wires, cut into separate grids and stretched to the required size, and deposited into a tray. You will notice that at no time are they touched by hand. Once again, inspection ensures that high quality levels are maintained. This is an anode being placed in position. The function of the anode is to collect the electrons given off by the cathode. Here in the power press room, anodes are stamped from flat metal strip. In the case of the anode we have just seen, this machine stamps out 2 separate halves, stitches them together, and deposits the finished component into a bin. Here are the separate stages. Anodes are made in a variety of shapes and sizes to comply with the requirements of the various types of valve. Some anodes are made in sections which are later joined together by welding. Here is one type for a valve, and another for a cathode ray tube. After the anode has been positioned, another mica is placed over the free ends of the various components to hold them in the correct positions, and the metal lugs are bent over to form a rigid assembly. At this point, the assembly is known as the cage. There are many different types of valve, and therefore many different methods of assembly. Here you see valves being made by traditional methods. It will be obvious that the standard of quality obtained depends largely on the skill and dexterity of the operator. Our demonstration valve, however, is being made by the latest hand assembly method. This method uses mechanical aids to assist in the threading of the various components. These not only ensure better quality, but also make the job easier to perform. Even left-handed operators find no difficulty in using these machines. Even in valve assembly, a measure of automation has been achieved. This is the cage of valve type ECC82 being made entirely by machine. Slides pass along the machine, receiving in turn the first mica, the first grid, followed by the first cathode and the first anode, completing half of the valve. Now the second grid, the second cathode, and the second anode, all held in place by the second mica. It is checked to ensure proper seating. The third mica to prevent vibration. Anode clamping to make the assembly rigid. First cathode tail is welded, and lastly the second cathode tail. You will remember that we left the construction of our demonstration valve as the operator was completing the cage. Whilst we've been looking at the fully automatic machine, the cage has been transferred to another operator who is welding the grid 1 strip, inserting the heater, and welding the cage to the valve base. Let's look now at these operations in more detail. First, the strip, which is used to connect grid 1 to one of the base pins. And now, the heater. Heaters are made from spiralized tungsten wire wrapped around a molybdenum core and wound onto spools. Here is the heater department, in which the spools are placed directly onto this machine, which automatically cuts the wire to length and bends it to the required shape. The bent heaters are now loaded into racks and passed to another operator who immerses them in a bath containing an insulating material. She next transfers the racks to a glow box where the coating is baked on by passing an electric current through the heaters. Here again, a machine has been developed which not only automatically cuts and shapes the heaters, but also carries out the operations of coating and glowing. You will remember that during the manufacture of the heater wire, the fine tungsten filament was wrapped around a molybdenum core which served as a mandrel during the winding and as a support during the subsequent operations. As this core is no longer required, it is removed by immersing the heaters in a bath of strong acid, which dissolves out the molybdenum, leaving only the coated tungsten spiral. The cage assembly is now ready to be welded to a base. This is the part of the valve which will later be plugged into a valve socket. Many types of base are made, but the modern glass base is now the most widely used. It consists of a circular glass pressing through which pass the metal pins which will be used later for the electrical connections. The bases are made on this type of machine, the pins being automatically fed from a hopper into the molding head. At the next position, a glass ring called a bead is fed from a hopper and placed round the pins. The head moves through a series of burners. The glass becomes softened and a toothed wheel presses it between the pins. At the first pressure, the glass is flattened. And at the second, the final shape is imparted to the base. Cleaning chambers now remove oxidation from the pins, and the finished base is automatically transferred to a conveyor belt, which carries it to an inspector. Before leaving the process of base making, it may be interesting to see how the various parts of the base are made. First, the glass portion which begins its life in the mixing room, where carefully weighed amounts of the raw materials are placed into a hopper. After the contents have been thoroughly mixed, the hopper is taken to the furnace room and placed in position on a melting tank. An automatic device gradually feeds the raw materials into the tank, which is heated to approximately 1400 degrees centigrade. Each furnace runs night and day for many months and only stops when a tank needs to be rebuilt. At the other end of the huge tanks, the glass is drawn off in the form of tubes of various sizes, an internal current of air keeping the molten glass in tubular form and controlling its diameter. As it ascends, external air streams cool it and control the thickness of the wall. Passing through holes in the ceiling, the continually rising columns of glass emerge into an upper room. Here the tube is cut into standard lengths, and each length is gauged and weighed to check its dimensions. These lengths are again cut into pieces of various sizes during the manufacture of many types of glass components in valves, cathode ray tubes, transistors, etc. Tubes of smaller diameter are cut to the correct length by means of this automatic apparatus. The base also contains metal pins of a special construction. These are made in the wire factory from several different kinds of wire, cut into short lengths and welded end to end. To understand why this is necessary, let us examine a typical pin. First, the thicker portion. This is the part which will be pushed into a valve socket and therefore must be strong. Secondly, the center portion, which will be buried in the glass. This must be made of a metal which will expand and contract at the same rate as the glass, otherwise the base would crack or leak. And finally, the electrode, which completes the electrical connections in the valve. This machine is cutting and welding the pieces together and packing the finished pins into boxes ready for dispatch to the base-making department. Now the bases are transferred to the cut and bend section, and here we see this operation being carried out. The base electrodes are cut to length. Then they are inserted into another machine, which bends them into the correct positions to mate up with their respective components in the cage assembly. Returning to the assembly section, we see the base being welded to the cage. All the electrical connections are now made. The getter and cooling plates are also welded on at this stage. The only component still to be added is the glass bulb. In the glass factory, the bulbs are made by placing lengths of tubing into a machine, which seals the end of the tube, forms it to the correct shape, cuts off the required length, and flares and polishes the cut end. The finished bulbs are deposited onto a conveyor belt and transported to a tubulating machine. This machine attaches a hollow stem to the bulb, which will be used later to extract the air from the valve. The machine automatically transfers the bulbs to a chain conveyor. Every bulb is tested for leaks by means of a powerful electric spark, which will find even the slightest defect. Should a leak be found, the machine automatically rejects the bulb. The inspector subjects each bulb to a thorough visual check. Only bulbs which are of good appearance are allowed to leave the department, any chipped or misshapen ones being rejected. After washing, the bulbs are stacked to await dispatch to the valve factory. Here in the bulbing section, we see them being fitted to a valve assembly. The next step is to seal the assembly into the glass bulb and then pump out the air, so forming a vacuum. Here is the sealing machine which performs the first of these operations. Blowpipe flames soften the glass at the junction of the bulb and base, fusing the two components together. The valve is next transferred to a rotary pump. The machine revolves and air is pumped out of the valves as they pass through coils carrying a high-frequency current. This heats up the metal parts of the valve, assisting in the evacuation process. At the last stage, the getter is fired. This releases barium, which condenses on the inside of the bulb. Its function is to trap and absorb any minute traces of gas which may be left in the valve. When evacuation is complete, the stem is sealed off and the valve removed from the pump. On the latest type of machine, the bulbing is done by the machine operator. The valves are automatically transferred from the conveyor belt to the sealing machine and then to the pump. To complete the treatment of the valve, it is now activated in a device known as a screen. This causes chemical changes to take place in the cathode coating and is necessary in order to make the valve work. Every valve undergoes a series of tests to ensure that it meets the high standard of quality required. This inspector is checking that there are no loose connections in the valve. After further testing, stacking of the finished valves brings the manufacturing process to an end. However, as a further safeguard of the customer's interests, every batch must receive the approval of an independent authority known as Test 2 Department before leaving the factory. In addition to the routine checks and tests at every stage of manufacture, yet another department is continually testing batches of completed valves selected at random from the production lines. This independent testing ensures that standards are maintained. After acceptance by Test 2 Department, the valves are packed for dispatch to Croydon Stores Unit, where they will be individually marked and boxed ready for distribution to the trade and their eventual use in radio and television. That, then, is how a typical valve is made. On our tour of the factory, we have seen how the never-ending search for better techniques is being pursued in every department. It is this constant seeking for perfection which has resulted in the Blackburn Works becoming the largest valve factory in Europe today. It is a story without an end, however, for even as this film is being made, still further expansion is taking place. This process of continual development will be maintained as we face the demands of the future. No matter what these may be, we can be sure our people will meet them, and in so doing, will go on to write yet another chapter in the Blackburn story.
This is a film about thermionic valves, and more particularly, about how they are made. You're no doubt familiar with this, an essential component of your radio or television receiver. And with this, its conventional representation in a circuit diagram. This particular valve is a pentode, and you will recognize its various parts: the envelope, the heater, the cathode, the control grid, the screen grid, the suppressor grid, and the anode. Now let's look at the actual parts and see how they're assembled into a complete valve. This is one form of cathode. It is a flat nickel tube, coated on the outside with an emissive material, a mixture of the oxides of barium and strontium. Here is the heater. Spiralized tungsten wire, only 70 microns, or a little over 1/500th of an inch in diameter. It is bent into a V shape and is coated with an insulating layer of alumina. These are typical grids, flattened spirals of fine molybdenum wire, wound on two stout backbone wires. In the pentode type of valve, there are three grids: the control grid, the screen grid, and the suppressor grid. The anode in this particular valve is stamped out of sheet metal in one piece. It is blackened on the outside to help dissipate the heat developed in the anode by bombardment by swiftly moving electrons. These are mica discs carrying metal screens, and the electrodes you've seen are assembled concentrically between two of these discs. For purposes of demonstration, the operator's movements have been slowed down, and jigs are not being fully used. First, the cathode is fitted in the bottom mica. Then the control grid. The screen grid is next. Now the suppressor grid is put in place. The anode is added. And the top mica goes into position. After fitting one or two more small components, the valve assembly is ready to be mounted on its base. The base is a glass disc holding 9 connecting pins to plug the valve into the set, and 9 corresponding wires to which the various electrodes are connected. The glass base is made up from these components: a short length of glass tubing and these connecting wires. The connecting wires are made in 3 parts. First, the valve pin. Secondly, the connecting wire. And between them, a short length of metal, which has the same overall coefficient of expansion as the glass, and which therefore makes a good airtight seal where the wires pass through the glass. Now look at the finished base again. You will see that the wires are cut and bent to the exact positions to receive the lower end of the various electrodes. Now assembly and base are fitted in a jig, where they are held in the correct position so that they can be joined by spot welding. When all the connections have been welded, the assembly is taken out of the jig and a few further components added. The heater is threaded through the cathode tube and its ends welded to appropriate wires in the base. This small plate helps in dissipating heat by radiation, so keeping the control grid cool and reducing the risk of grid emission. It will be welded on the control grid backbone wires just here. This gauze cylinder acts as an electrostatic screen. This additional mica disc keeps the assembly central in the bulb. the getter, which contains a small quantity of chemical material that is evaporated after the valve has been pumped, combining with the small remaining traces of gas, so perfecting the vacuum. The getter plate which carries the getter. It is mounted at the top of the assembly and serves not only to support the getter, but also to prevent the getter material condensing on the valve electrodes. Here is the getter welded onto the getter plate. The bulb is a glass tube with one end closed, and to this is attached a thinner tube in such a way that a passage is opened between the bulb and the tube. Let's push a wire through to show you. It's through the thinner tube that the air is withdrawn from the valve during the pumping operation. Now the electrode assembly is placed in the bulb, so. The junction between the base and the bulb is then heated, so that the two glass surfaces fuse together. The valve is then plugged into the pumping machine. The air is removed and the valve sealed off, leaving a short pip at the top, which is the remains of the pumping tube. The dark area on the inside of the bulb is due to the firing of the getter. Now let's go to the factory to see the valves actually being made. Of course, it isn't merely a matter of making just one valve having the required characteristics. Huge quantities must be produced, and each valve must give exactly the same performance. To control quality right from the beginning, production starts with chemicals, mineral salts, metals, and other raw materials, often in their most elementary forms. Here are the raw materials of glass: sand, red lead, soda, and a proportion of broken glass, technically known as cullet, which are melted together in the glass furnace. Many of the glass parts used in valve manufacture are made from glass tubing. From the tube-making machine, a column of molten glass is drawn upwards, an internal blast of air keeping the glass in tubular form and controlling its diameter. As it ascends, external air streams cool it and control the thickness of the wall. Here, the now solid tube is cut to standard lengths, and each length is gauged and weighed to check its dimensions. Bulbs for receiving valves are made from short lengths of glass tube. The tube is cut to length on one machine and closed at one end on another. Now the smaller tube is fused to the closed end. It is through this smaller tube that the air is removed from the bulb in the final stages of manufacture. After each stage in which glass has been worked, it is annealed by raising it above a certain temperature and then cooling it gradually, thus normalizing any strains set up in the material. Each bulb is inspected, and any which show defects are ejected. In this test equipment, a high-tension discharge is produced between two electrodes. When a good bulb is placed over the probe, the spark is extinguished. But if there is the slightest crack or flaw, the discharge sparks through, the faulty bulb then being rejected. Besides bulbs, all kinds of small glass sections are made. Here are a few examples. At every stage the components are checked. Here the thickness of the glass is measured with a micrometer. In other parts of the factory, other components are being made. So let's take a look at these now. We shall be meeting the glass again at a later stage. The heater is made from tungsten, and tungsten is the metal obtained from scheelite. The scheelite is weighed and tipped into a ball mill. Here it is ground continuously for 7 days to reduce it to a fine powder, which then undergoes various chemical treatments which yield pure tungsten in powder form. The tungsten powder is weighed out into suitable charges. It is placed in a steel mold, carefully leveled, and packed down. The mold goes into a hydraulic press, and a pressure of about 100 tons is applied. When withdrawn from the mold, the metal is in bar shape, but as yet it is very fragile. So the bar is now sintered. It is heated to a very high temperature by enclosing it in an atmosphere of hydrogen and passing an electric current of between 2,000 and 3,000 amperes through the metal. A temperature of 2,700 degrees centigrade is obtained. The tungsten now has a crystalline structure. The first process in wire making is swaging, that is, hammering the bar so that it becomes thinner and longer. In these machines, metal is heated and beaten with hammers in rapid succession, making it thinner, longer, and rounder. It is now ready to be drawn to still smaller diameters. Lubricated with graphite, the wire is heated and pulled through tungsten carbide dies by a chain-driven mechanism. This sequence, lubrication, heating and drawing, is repeated with smaller and smaller dies until the diameter of the wire has been reduced to about 1/50th of an inch. From this stage, diamond dies are used, until after some 200 or 300 drawings, the original bar has been transformed into as much as 200 miles of fine wire, of diameters down to 6 microns, or 3/10,000ths of an inch. Such very fine wire cannot be measured by normal instruments. Its diameter is therefore checked by weighing a known length of wire. It is also examined for roundness under a microscope. Molybdenum wire is also required in valve manufacture. For example, it is used for valve grids and filament mandrels. The molybdenum wire is produced from its ore in a very similar way to tungsten. Coiled tungsten wire for valve heaters is produced by winding the tungsten wire on a mandrel of molybdenum wire, and later dissolving the molybdenum with acid. Now for some other valve components. Mica discs are stamped out of sheet mica and are checked for size and position of holes by projecting their image 30 times full size onto an illuminated screen, where the dimensions can be measured to within 1/500th of an inch. After this, the discs are examined, and any broken ones rejected. Anodes are stamped out of sheet metal, usually nickel. This machine produces complete anodes, accurately stamped, bent to shape and lock-seamed from flat nickel strip. Each single anode is carefully inspected. Now for grids, which are being made in long lengths on this machine. As the machine spins round, it anchors the fine grid wire into notches made automatically in the supporting wires. The lengths are cut into individual grids. The operator controlling the machine can see them enlarged on a ground glass screen. Each grid is stretched to correct size and shape, and its dimensions checked in a gauge. Heaters for indirectly heated cathodes are made from tungsten wire. The wire is bent to an M or V shape. These wires are next clipped into frames, immersed in a bath containing insulating material, which is later baked on by passing a current through the wires. Nickel cathode tubes are cut to length, mounted in frames, and sprayed with barium and strontium carbonates, from which the emissive surface is produced later on. In this case, the heaters are inserted into the coated tube at an early stage. Now you can see that most important component, the getter, being made. It is being electrically welded onto a finished assembly. This machine makes the lead-in wires, which you will recollect are composed of three parts: a stout pin for the valve holder, a thinner wire to which one of the valve electrodes is welded, and between them a short length of wire which forms an airtight seal in the glass base. The lead-in wires are loaded into the base-making machine and are automatically fed, 9 at a time, into a jig. A glass ring is placed in position round the wires, and the jig is made to revolve under gas flames. The glass softens, and the machine presses it to form the base. When cold, the bases are inspected. The support wires are then cut to length by one machine, and in the next they are bent to the positions they must assume for the components to be welded to them. Here's a valve assembly section in the thermionic valve factory. There are many different types of valve, and therefore many different forms of electrodes, and many different methods of assembly. These are just a few examples of the operations involved. You have seen many of these operations earlier in this film, performed deliberately and slowly to show you what is done. Now that you see the valves assembled at production speed, you can appreciate that these delicate operations demand great skill and dexterity on the part of the operators. The next step is to seal the assembly into the glass bulb and then pump out the air, so forming a vacuum. Blowpipe flames soften the glass at the junction of the envelope and base, and pressure is applied to form the joint. The valves are transferred to this machine, in which they are pumped continuously to create the vacuum. They pass through a heated tunnel which helps to drive off the gas. Then through coils carrying high-frequency currents which heat the metal parts and drive off more gas. A current through the heater heats the cathode and so reduces the coating on the cathode to oxide, thus forming the emissive surface. High-frequency currents also evaporate the getter to absorb the last traces of gas. After being sealed off, the valves are mounted in racks and are operated for a period under controlled conditions. During this time, further changes occur in the cathode coating, resulting in improved emission. Lastly, the valves are tested for emission, vacuum, insulation, and operating characteristics. In the automatic high-speed tester, the valves are plugged into holders which move to a number of successive stations. At each station, a different test is applied, and if a valve fails in any one of these tests, an automatic hand removes it from the machine. In addition to these routine tests, the Quality Control Laboratory continuously tests batches of valves selected at random from the production line. Any falling off in quality is detected at the earliest possible moment, so that steps can be taken to correct it before the trouble can assume serious proportions. That, then, is how the many different parts of a valve are made and put together, and how valves are manufactured under mass production conditions. We hope we've shown you enough to indicate that valve manufacture is a job for a team, that the research worker, designer, plant engineer, laboratory technician, supervisory staff, and the operator all have essential parts to play. So when you next listen to the radio, watch television, or possibly work with equipment employing thermionic valves, perhaps you'll remember something of what goes into the production of these outwardly simple, yet in reality complex, devices.